Hello, and welcome to our video on solving indeterminate beams with kinematics and deflection tables. You were told in statics that we just can't solve these, but now we're learning that we can. We just have to do a little extra work. All right, so for this particular beam, it looks like a simply supported with a pin at A and a roller at C, but we have this extra roller also at B. So when we draw our free body diagram, we see that we're going to have an AY, a BY, and a CY support reaction along with the AX. So obviously our first step, we can just jump right in and do our statics. And the easiest equation to start with would be to sum forces in the X equal to 0. And so of course AX is going to be equal to 0. Now I want to go ahead and sum moments, and I'll sum moments at A equal to 0. And I'm going to pick clockwise as positive for this particular solution, but I don't have to. It's just what I like to do. And I want to stop for a second and remind ourselves that the resultant of that uniform load W is just going to be WL. So I can write out the resultant as WL, and it's going to act at L over 2. So I'm going to have WL squared minus 2, then minus BY times 2/3 L minus CY times L. And then I could sum forces in the Y, or I could go ahead and just sum moments again. So I'm going to sum moments at C. This time I'm going to go counterclockwise because, again, it doesn't matter. It's unique for each moment expression. It's just a way to add like terms. But what we find when we write out the moment expression at C, we have an AY and a BY in that expression, so we can't solve for anything. We've got a BY and a CY in our sum moments at A expression. So we're sitting still with just 2 equations and 3 unknowns, and that deserves a frowny face. Now you may have said, well, wait. We didn't need to sum forces in the X, right? Because we only get 3 equations in 2-dimensional statics. We didn't need to sum forces in the X. We could have looked at that and said that AX is equal to 0. So we could have come back and just summed forces in the Y, and we'd be done. Well, it'd be nice, but it doesn't work like that. Because when you looked at AX and said, I know that's equal to 0, you just summed forces in the X in your head. So you used the expression regardless. If you wrote a sum forces in the Y equal to 0 and said AY plus CY plus BY equals WL, it's totally accurate. But now I would encourage you to try that and solve your 2 moment expressions and the sum forces in the Y expression simultaneously, and you're going to get back out non-useful info. You'll get back out AY equals AY or 0 equals 0. You won't actually ever get a value. And that's why we need some new tools. And so what we want to actually do is introduce something called kinematics and the redundant force method. And kinematics is what we call the geometry of the motion. And in our case, the motion is deformation, and it's the deformation in our beam. So we could say that kinematics is the geometry of the deformation. And let's remind ourselves, so go back and look at our original beam. We can change where we label things so we have a little bit of space. And now we can draw in the deformed shape. And instead of just smiling, like the beam would do if the roller at B wasn't there, we actually go back up and have 0 deformation at B, and then have a little smile between B and C. So we want to use what we can see here in the geometry of that deformation. Now, I also said that we should use the redundant force method. So here's what the redundant force method does. It basically acknowledges or notes that we have more vertical support reactions than we need. Right now we have 1 extra. We have AY, BY, and CY, and one of those could go away. One of them is redundant, all right? So once we notice that one is redundant, what we want to do, and that's redundant for the beam to be stable, okay? So what we can do is we're just going to remove one of the redundant supports. Just take it out. and turn the beam back into a statically determinate beam. But then we want to use superposition. We want to add another beam that's identical to the new one we created as far as supports. So it's still determinate, has the same supports, but then we're going to add back in that redundant support that we removed as a force. Okay, so we get that same behavior that the redundant support was giving us. So we really want to see what that looks like. And I'm going to suggest that we choose BY as our redundant, simply because, well, it'll come clear later, we have deflection tables for beams that have supports at A and C. We don't have deflection tables for beams that have overhangs, as if we had a support at A and B only or B and C only. So what I want to do is quickly draw out for you, and we'll just quickly get them down. Here would be our two beams. And this would be what I'm saying. So we removed BY, and now we just have a simply supported beam with a uniform load. When it deforms, we see a smile. If I then add to that, so we're going to superimpose or add the behavior from a second beam. This is really important. Notice it has the exact same support condition. So I kept a pin at A and a roller at C in my second beam. And then I'm going to add the redundant support BY as a load. And we can see that that beam has a deformation. The kinematics of that beam is a frown. And if we were to look at what the deformation was at L over 2 for our second beam, and we look at what the deformation is for our first beam at L over 2, so we can call those beam 1 and beam 2, and we look at our original beam, and our original beam at L over 2, at 2L over 3, at 2L over 3, we know the deformation of that one is 0. But beam 1 and beam 2 both show some amount of deformation. Well, our whole goal is to create compatibility. We need to enforce compatibility. And what we mean by that is that if we can say, we want to be able to say that we can add beam 1 to beam 2. We can superimpose them and equal the original beam. Get the same behavior. But that only works if, and only if, the deformation in beam 1 at 2L over 3 plus the deformation in beam 2 at 2L over 3, when those add together, it equals 0. Because that's what happens on the original beam. And if we can enforce that, if we can enforce that behavior of the deformation, then we can solve these two statically determinate beams and actually find BY by using this extra compatibility equation. So the easiest thing to do to find our V1 and V2 deformations at 2L over 3 is to actually just go into our deflection tables. So it's pretty handy that we have those available, and using the pin and the roller at A and C, the tables are available to us. So we jump over to the table, we have our simply supported beam and our expression in terms of X for the elastic curve, and we have the same thing for that point load. Our point load here is going the wrong direction, but that's okay. Now, it turns out that for the point load, the expression for the elastic curve is valid from 0 less than or equal to X less than or equal to A, where in our case A would be 2L over 3, 2/3 L. But if we plugged in, so we could use the equation in the elastic curve column and just plug in X equal to A, they've actually already done that for us, and that is the deflection shown in the deflection column. So they've just plugged in the A. So either one will work for us. So if we were to go back to our, back to where we were, and now we can actually start looking at the expressions. So we had found that the displacement, the equation for the displacement was negative Wx over 24 EI times the quantity of x cubed minus 2l x squared plus l cubed. So let's just plug in 2l over 3 into that equation. And if we multiply everything out, so now everything's in terms of L, and we solve that, we can actually find that the displacement from beam 1 at 2L over 3 is negative 11 WL to the fourth over 972 EI. Now we can do the same thing for our second beam. Now we're going straight to A, and let's redefine what A and B are per the table on our beam there. But in this case, we have to add in that plus symbol. It is plus PBA over 6EIL, not negative. Because in this case, our beam is going up. It's deflecting up in a positive direction, so we have to change the sign of what was in the table. But that's our prerogative to do. We have to look at the observation of the real behavior. Now, if we put in 2L over 3 for A, which means for B, we're putting in L over 3, and we plug in all of our values into this equation. We're going to get everything now again in terms of L, and we're going to get back out that the displacement for beam 2 at L over 3 is just positive 4 BY L cubed over 243 EI. And we have that BY because, of course, our P is the redundant force that we put in to mimic the support reaction at B, BY. Right, folks, we're almost done because we imposed that compatibility equation. So if we go back and just now solve our compatibility equation of the displacement from beam 1 at 2L over 3 plus the displacement at beam 2 at 2L over 3 has to equal to 0, we're basically now saying negative 11 WL to the fourth over 972 EI plus 4 BY L cubed over 243 EI has to equal 0. Now the EI's will cancel. The L cubed in the second term will cancel with all of the L's but 1 in the second term, since the whole thing's equal to 0. And notice the only unknown in there, because we're assuming we know the load W, we're just holding it as a constant, the only unknown is the reaction BY. And we can actually find BY equal to positive 0.688 WL going in the upward direction, and we have our answer. And now, if we look back at our statics equations, if BY is known, we're just left with two equations and two unknowns, AY and CY. So just put BY back in your statics equations. And then, if we look back up at those equations, we can then actually get back that AY is 0.271 WL in the upward direction, and CY is 0.041 WL in the upward direction. And so you just solved a statically indeterminate problem by taking advantage of the motion of the geometry, or the motion of the deformation, the geometry of the deformation, and what you know about enforcing compatibility. Congratulations.